So now I'll talk about simple plane flow. And we'll do two examples. The first example is that of a simple parallel shear flow, and we've encountered that before. It's the case where you have your velocity field only varying in one direction. So it might be slower down at the bottom and then get increasingly faster, but it only varies with your x2 direction. So this is x1, x2, and then your velocity field, in this case, u is given as u1, a function of x2, and 0. Yeah, so this here is u1 as a function of x2. In this case, we only have one non-zero velocity gradient, and that's du1 dx2, and let's call that gamma of x2. So this is our velocity gradient, gamma. Gamma is our velocity gradient. And in this case, our vorticity is easily computed from the curl of u, and that's omega, and it is simply 0, 0 minus gamma. So your axis of rotation is out of the x1, x2 plane. And we know that the angular velocity is always half the magnitude of the vorticity, so angular velocity in this case is minus gamma over 2. That's the rate of rotation of a given fluid element. So let's consider a fluid element that is aligned with our axes x1 and x2. So that translates over time, and it deforms the bottom part. Okay, let me just draw the original and consider how this shape changes. The bottom section, let me label these points A, B, C, D. The bottom section AB will not change, right? You have a uniform steady flow, should add here, steady flow, and it's uniform in the x1 direction. So this one will not change. AB will, A dash B dash will be the same. But now here you go from C to C dash, right? And that rate of rotation here, this angular velocity is simply gamma, or rather minus gamma, since we're going in the negative direction. And here the angular velocity of AB is 0, since it doesn't change. Yeah? So AC rotates by minus gamma, AB doesn't. And as a result, our average angular velocity, which is a half angle of rotation, angular velocity up here minus gamma minus 0, is simply minus gamma over 2, which is exactly what we found up here from the vorticity. So that's where that came from. Now let's consider our strain rate tensor, Sij. As a reminder, it's defined to be a half dui dxj plus duj dxi. And in our case, if we plug in du1 dx2, that's the only one we have, you find that, what do we find? We find S11 equals S22 equals 0, and S12 equals S21 equals gamma over 2. So our, in vector form, our S tensor looks like this. So no diagonal elements, just off-diagonal elements, which means there is no elongation and pure shear. That's what this fluid element that's aligned with x1, x2 is experiencing. So we know that we can diagonalize S. We did that last time. So basically try and find the principal axes of this deformation. So let's rotate the coordinate system. We're rotating the coordinate system. Which is equivalent to finding we're rotating the coordinate system, which is equivalent to finding the principal axes of Sij, or also we're diagonalizing the strain rate tensor. So, and we did that in the tensor chapter, and we realized that if you have in 2D a flow that has no diagonal elements, just off diagonal, you can rotate it by 45 degrees and you get and x1 dash and x2 dash are your new principal axes. So in this case, and we've done this before, S dash is gamma over 2 minus gamma over 2, 0, 0. So see the tensor example for diagonalizing Sij. And we note here that Sii, which is the trace of S, so that's gamma over 2 minus gamma over 2 in this case, it's the sum of the diagonal elements, is 0, and that's the same as Sii dash. So there's no area change in the fluid element, which is good since the trace is an invariant for our second order tensor. Yeah, so that just confirms that. So let's consider what happens to a fluid element that is aligned with the axes x1 dash and x2 dash. So here's our original one that's aligned with x1 and x2. And now let's consider an element, also a square, that's aligned with x1 dash and x2 dash. So the first element, as we saw, the original AB line doesn't deform, but the AC line does deform, whereas in our new coordinate axis, you can show that this angle here, that started out as a right angle, remains a right angle. So the angle between the segments doesn't change. Angle between segments remains the same. Which means there's no shear, pure elongation of the segment along dx1 dash direction and pure contraction along x2 dash. And the final thing to note for this flow is that our element of vorticity omega 3 remains the same in our new coordinate system. So the direction doesn't change. It's still out of the x1, x2 plane, and the magnitude is invariant. So basically the rate of rotation of the fluid element is the same in both coordinates, and that's good because omega is a vector, and the magnitude for a vector is always invariant. So in summary, while the fluid element that is aligned with x1, x2 undergoes pure shear and no elongation contraction, the fluid element that is aligned with the principal axes of our strain rate tensor, x1 dash, x2 dash, undergoes pure elongation, contraction, and no shear. But both of these elements undergo the same angular velocity rotation, the same rotation in terms of their angular velocity.